Hi, Assalamualaikum warahmatullahi wabarakatuh, and good day to everybody. I'm Dr. Siti Rabiatul Aisyah binti Idris. So today we are going to continue our lecture, which is still under CO1 with title Analysis Stress and Strain Problems in Structural Members under Axial Loading. And this is the chapter objective as well as lesson objective for this topic, for this subject. But then for today, we are going to learn on how to calculate the deformation of stress and strain of structural members subjected to simple loadings, for example, axial loading and also direct shear. If you still remember these structures, example of structures from our previous slide, can you guess what types of materials are these structures being made of? Anyone would like to guess? Yeah, you see there are various types of materials being used to produce these types of structures or product, and the types and different types of materials will make the products perform differently. This is because it depends on these types of loading. For example, direct force, shear force, torsion, bending moment, fluid pressure, temperature difference, and these types of loading we are going to see, and we are going to calculate its effects on the structures or the components. For example, if you still remember the concept of strain in statics or in engineering materials, strain is used to describe the deformation of a body by changes in length of line segments and the changes in the angles between them. You see, after the loading being applied to the structure, it will change in shape, and the properties of the materials or structure itself will keep changing. And this is the formula for normal strain. Epsilon equals to delta S prime minus delta S divided by delta S. Delta S prime represents the elongation after the deformation. Delta S represents the original length. Other than normal strain, there's also known as shear strain exists on that structure after the deformation. Shear strain is the change in angle that occurs between two line segments that were originally perpendicular to one and another. If you look at the segment there, if the forces being applied on that segment, you see the segment itself being distorted a little bit, and therefore the shear strain being represented as gamma at that point. So that is known as shear strain, and the formula you can see as stated in the slide here. However, for someone, we are not going to calculate the value of shear strain, but you are going to continue to calculate the value of strain in SOM 2. Now, let's move on to design properties of materials. In engineering materials, we know that there are two types of metal exist, which is metals and non-metal, of course, like ceramics and plastic and so on and so forth. And to test these materials, we need to conduct which is known as tension test. From there, we will get the value of stress strain curve there, which stated the area for elastic and plastic region. Later on, we are going to look at that graph and how to get the value of stress strain there. Other than that, in design consideration, we need to consider the material properties and also physical properties like elastic modulus, yield strength, tensile strength, ductility, and CTE. There are also different types of materials that I've mentioned in our early slide just now, like metal, ceramic, polymers, and other groups like composites, semiconductors, and so on and so forth. So these types of materials actually perform in different ways. And therefore we need to decide what types of materials that is going to be used in our own design. And the performance of those materials that have been listed just now are actually depending on 3 items, which is number 1, processing methods, number 2, structures, and number 3 is properties. For example, if you choose different types of processing method to produce a same structure, which is metal, for example, but the structure itself will changing, and this one will affect its properties or its strength, which finally it will affect the final performance of that structure. Therefore, we need to be carefully choose these 3 elements because they are actually have a relationship between each other. And the strength of materials being calculated based on its ability to sustain the load without undue deformation, and this can be calculated through experiment or also known as tension test. And when we want to conduct tension test, then we need to know all these formula and the parameters like sigma equals to P over A, like the one that I've mentioned in lecture 1 and in last week lectures. And this is the machine that is used for a tension test, to conduct tension test. And this machine can be found in Material Science Lab, University Malaysia Pahang, FTKMA. From this figure, you can see that the specimen being placed here at this point, and it is gripped with specimen grip. After that, the value of loading being inserted in this computer, then the specimen will be pulled according to the data insert in the computer or in the software itself until it fails. From there, we will get these types of graph: shear, stress strain graph, and this one actually represent graph shear stress strain graph for metal, because if you look at here, there's a elastic region and plastic region. Starting from this one is elastic region until it fails at this point. You see, this is the elastic region, and after that, beyond that point, this is known as plastic region. At the end of plastic region, which is before it fracture, it start to necking there. After that, it will lead to failure. You see, different types of materials will have different stress strain curve, they call it. So for example, if you're taking a composite for your specimen, then the graph will have no plastic region. It will fail exactly in elastic region, so the graph will be straight or linear graph. And this one for aluminum. The rest of other types of materials you can study on your own. Now let's look at on how to solve a problem using stress strain curve. For example, from the figure here, the question asks you to find the following items. Number 1, the modulus of elasticity. Now, how to solve this problem? A, modulus. The question asks you to find the value of modulus of elasticity. If you still remember, the value of modulus Young equals to sigma divided by epsilon. Sigma is stress, epsilon is strain, which is can get from the slope of the graph. So if you refer to the graph just now, you can see that the value of stress sigma 2 and sigma 1, which is at this point, sigma 2 at elastic region. Remember, modulus elasticity only exists in elastic region. So we get this one sigma 1 and sigma 2. So which is y-axis and this one x-axis. From there, just substitute into the formula, then you will get the value of modulus of elasticity equals to 93.75 gigapascal. Move on to question B. The question asks you to find the yield strength at a strain offset of 0.002. So if you look at the graph itself, this line, okay, this is offset 0.002. So the intersection with the stress strain curve is at approximately 250 megapascal, which is the yield strength of the brass. Again, if you look at the graph here, at this point 0.02, and then taking it back here, so you'll get approximately 250 megapascal. Move on to next question. The question asks you to find maximum load. We know that the equation, the formula for sigma stress equals to P over A or F over A. And rearrange back the formula, then you'll get F equals to sigma A. And in the question, the value of diameter is given to you. So from there, you just substitute all the formula. Substitute all the data into the formula, and you'll get the value of F equals to 57.906 kilonewton. Last but not least is question D. The question asks you to find the change in length or delta L. Formula for delta L is equals to epsilon L naught, and the value for L naught is given. Same goes to sigma. Sigma can be obtained from the graph because epsilon is given to you. Epsilon equals to 0.06. From there, you'll get the value of sigma there. So just substitute into the formula, and you get the value of delta L. Okay, so another part in designing a structures or components or product is other properties, which is CTE. The deformation due to CTE is delta T equals to alpha delta T L. Well, alpha is the coefficient of thermal expansion, and delta capital D here represent a change in temperature, and L is the length, and this one delta T is the linear expansion or contraction. Now we are going to see the deformation on the structures after being subjected to axial loading, and then we are going to look at on the design stress, factor of safety, thermal stress, and also its application. The formula for deformation delta due to axial force is that delta equals to PL over E. The one that you've seen in the previous slide just now, deformation due to change in temperature. So this one due to axial loading. So all this calculation basically is in elastic region. And if we get the value of delta as positive, then it is considered as elongated. Whereas if it is in negative value, then it is actually contracted. So let's look at the example. For example, this bar being have 4 sections, section AB, section BC, and section CD. We know that the formula for delta due to axial loading is equals to PL over AE. Now, how are we going to solve this problem? Firstly, we need to cut all the sections one by one. It's either from point A until point D, or starting from point D until point A. So it's up to you which point that you want to start, but please be consistent on how you cut the value. You cut the section. Now let's see this example, because this example actually combining both sides, cutting from point A to D and cutting from point D to A. Now for first step is that you cut from point A until exactly before point B, which is finally you get this structure. From there you need to draw free body diagram. After that, you need to take the total forces in x direction equals to 0. Then you'll get the value of PAB, which is equals to 5 kilonewton. After that, you need to cut again from point A until exactly before point C there. So you will get this structure. From here, same steps, whereby you need to summarize the total forces of x direction equals to 0. For me, I would prefer to take the positive direction to the right, positive. So from there, you'll get the value of PBC, which is equals to 3 kilonewton. And last but not least, you can either cut from A until to section exactly before point D, or you can do the other way around, which is cutting from point D and stop exactly before point C. From here, from this free body diagram, you'll get the value of 7 kilonewton for PCD. After that, you need to summarize all the sections by putting into this formula. So altogether, you will get 3 sections. Maybe that formula is not really clear to you because there's no final value for that example. So let's look at this example, our next example. Let's read it together. The composite A36 steel bar shown below, made from 2 segments AB and BD, having cross-sectional area of AB equals to 600 mm square and ABD equals to 1200 mm square. Determine the vertical displacement of NA and the displacement of P relative to point C. So the first step is that we need to know how are we going to cut the section. Same steps as in previous example. First of all, okay, so for this example, I started to cut from point A until exactly before point B. So from there, you'll get the value of PAB, which is equals to 75 kilonewton. And after that, I start to cut again for section BC, starting from A and the section BC here. And from there, total forces in y direction is equals to 0. You'll get the value of PBC equals to 35 kilonewton. And last but not least is starting from point A until point exactly before point CD. Total forces from this free body diagram, you need to take total forces in y direction equals to 0. Then you'll get the value of PCD equals to 45 kilonewton. There's a student asked me, how can we know how many sections that we need to cut? Well, you need to cut whenever there's changes in cross-sectional area or the size of that structure, and whenever there's other forces acting on that section. From that, you need to divide into section. Okay. So from this information, just substitute into the formula for each section. By right, you have 3 sections: AB, BC, and CD. For this case, the value of Young modulus is given to you, which is equals to 210 power of 10 power of 3 megapascal. From there, just substitute all the information that you get from the section that have been cut just now. And finally, you'll get the deformation at point A is 6.101 times 10 power of -4 meter. And if you notice the value is positive, it means that the bar elongates and the displacement at point A is moving upward. Now what happens to next question, which is delta at point B relative to point C. From the diagram, from the free body diagram or section that you've cut just now, there's you'll get the value of BBC, and therefore just substitute the formula into the formula. So then you'll get the value of delta BC equals to 1.042 times 10 to the power of -4 meter. And this one also positive, which means that the segment elongates and B moves away from point C. So that will be all for this lecture 4. See you again in the next topic. Have fun and bye-bye.